In this video, we will discuss the impact of increasing penetration level of wind power plants on power system frequency stability. I will first describe the concept of stability. Let's start with the notion of power system stability. You might already be familiar with the notion of cost-benefit analysis, which in the case of electrical power systems deals with the performance assessment of the system over a long period. Cost-benefit analysis is based on a simplified modeling approach. In such approach, it is assumed that the devices and their controllers are able to fulfill a number of technical specifications. Hence, the modeling details related to their dynamic response are neglected, and the focus is put on the pre- or post-disturbance static performance of the system. By contrast, stability analysis refers to the study of the time-varying attributes of a power system, which can be judged by studying the dynamic performance of the system under a particular set of conditions and disturbances. Stability, in a few words, is the ability of the system to survive disturbances. That could mean that the system continues performing at the same operating point, or might be able to reach a different, yet stable, operating point. Let's look at an example in terms of a measured response. For instance, the voltage magnitude. If we solve for the power flow calculation, we get a value for the voltage at a certain bus. If the demand and generation do not change with time, you will get a flat response from solving your dynamic models. This means that we are operating around a stable equilibrium point. But if a disturbance happens, could be a short circuit or generator outage, then the solution of your differential algebraic equations-based model would not be a flat line, but actually a dynamic response. If the system returns to the same operating point after this behavior, then the system is said to be stable. If something happens, such a topology change, then the end operating point might be different than the original one. However, as long as the new operating point is close to the original point, the system can still be called stable. A system is called unstable when it goes into runaway situations, diverging uncontrollably from the original operating point, with no way of making return to the stable situation. This is the most basic form of stability assessment, which is looking at the time response of the variables in your system. Let's now talk about the different kinds of controls which can cope with different types of stability at different time scales. As you can see, there are two main types of controls: voltage controls and frequency controls. In addition, there are ancillary services which deal with restoring a system after a blackout. Again, a system is called unstable when it goes into runaway situations, diverging uncontrollably from the original operating point, with no way of making return to the stable situation. Let's now consider an example in which several synchronous generators and their control system have been phased out and replaced by renewable power generation, like wind and solar photovoltaic power plants. We assume the occurrence of a generator outage, which causes active power imbalance and is reflected in the system in the form of a frequency decrease. If the power electronic interface renewable generation is not equipped with a special control system to provide fast active power injection to mitigate the decrease of frequency, the system will experience a higher rate of change of frequency, or rock-off, which can adversely impact the remaining synchronous generators and trigger spatial protection. The frequency might also reach unacceptable values of frequency nadir, which might lead to load shedding, causing economic losses. For sake of further illustration, the impact of increasing power electronic interface large wind power plants is analyzed by considering a benchmark system with three interconnected synchronous areas. To illustrate the effects of increasing wind penetration, several simulations were performed by using a software package for modeling a simulation of the time response of the system in a time scale of several seconds. The simulations consider a number of operational scenarios, starting from a condition in which the system is fully supplied by conventional power plants with synchronous generators, until the condition in which synchronous generation remains only in area A. In other scenarios, an imbalance is produced by the sudden outage of the conventional power plant in area E, which represents 6.3% of the total generation. Let's now check a summary of the simulation outcomes. The left figure shows all simulations plotted together, and it clearly reveals different values of rock-off for the same level of kinetic energy. It is observed that the trend of the rock-off is such that the values are higher when the inertia or kinetic energy is low, which happens when wind generation replaces synchronous generators. This means that it is possible to establish a clear single-value relationship between the frequency response of the system and the overall system kinetic energy. However, when the system load demand increases, the frequency tends to respond more abruptly, I thought with the same trend, which is observed in the left figure even though the kinetic energy might be the same. As shown in the right figure, the nadir has a negative correlation with Rokov. That means the higher the Rokov, the lower the nadir, which is an expected consequence, since the Rokov measures how fast the frequency drops. To wrap up, in this video, we defined and classified the notion of stability in a power grid. We also explored the impact of increasing penetration of power electronic interface generation on the system stability of a power system. The dynamic behavior of the future power grid will be radically different. The operators will face unprecedented, highly variable operating conditions and will have to cope with the occurrence of faster dynamic phenomena and also with coupling of different phenomena. Significant research effort is needed to tackle the dramatic decrease of inertia and conventional sources of active and reactive power support. Developing power electronic converters that can help to successfully replace conventional generation and developing new control methods that can deal with fast dynamics and coupling of phenomena are the two most important research areas at the moment.